Hi, my name is also LaMontagne, and our team is the Pyro Pioneers, and our project is the Robotic Fire Extinguishment System. Our team members include Austin, Hank, Jackson, and Nathan, and we're going to go over four main aspects of how we design a robot, including software, electronics, 3D printing design, and our water systems. First, let us show you some demonstration videos of what the RFES can do. In the actual video, you need to tag me, bro. Socials.
The system communicates with the software across Wi-Fi using the client-server TCP protocol. The video feed and instructions sent to the system are running in different threads so that the video transmission is not blocked. Since the Raspberry Pi runs Python code well, we decided to use Python to implement this networking protocol. The Raspberry Pi will run a server, and the software on our machine will be the client connected to the server. Because we are using Python, the software UI is backed with PyQt library, as it is customizable, integrates well with Python, and has comprehensive functionality. With all these tools, we are able to send commands to the system, and the system is able to transmit live video feed and be displayed on the software. On top of the video feed, the water level inside the tank, the system temperature, and the battery level are displayed on the screen on the top right corner. There are three ways on how the operator can operate the system: manual mode, scripting mode, and autopilot. In manual mode, the operator can interface with the system using keys on the keyboard. The operator can control the movement of the system, the nozzle direction, and the pump. In scripting mode, the operator can program the system to execute certain commands. There is an inbuilt scripting language where the operator can write movement, spray, and nozzle direction commands, and the system will execute them sequentially. For loops are also supported in their scripting language. Lastly, when the system is in autopilot, the system will automatically scan for any fire around it. Movement instructions are sent to the system automatically. When it detects fire, it will start to maneuver to it by first centering the source of fire on its view. When centered, the system will start moving forward the flame until it is within its firing range. When the system is close enough to the flame, it will direct its nozzle to it and start spraying water. It will continue to do so until the fire is put out. When the fire is fully extinguished, the system will continue to scan its surrounding for any other sources of flame. This is all possible due to the image recognition model that was trained to detect fire. We use RoboFlow's API to achieve this. Since this image recognition model is computationally intensive to run, as soon as fire has been detected, it will pass that frame region to a tracking algorithm called tracking median flow to track the fire, which is much less intensive to run.
For electronics, this is what enables all of the functionality of our robot to work properly. To begin, we use the Raspberry Pi 4 to control all of the electronics on board, from the pump to the servos to the motors that drive the robot itself. We use GPIO pins on board the Raspberry Pi to control all of these functions, as well as receive signal data to just send back to the client. We host a server on board the Raspberry Pi which communicates all this information back and forth between the client. To power all the electronics on board, we use 2 batteries. We use this battery right here, which is 3 lithium-ion batteries, or we use a 6 lithium-ion battery pack down below. The battery pack down below supplies 12 volts, which we convert to 5 volts using this buck converter right here. We have 12 volts input here and it outputs 5 volts. And then we use this right here as a steady power supply to power the Raspberry Pi, so we have no brownout voltage errors like we were having at the beginning. To begin with the pump, we power the pump using 5 volts from the buck converter, which then is sent through this relay, and the relay is toggled using GPIO pins and a signal that is sent when we press spacebar on the keyboard. When we press spacebar, 5 volts get sent to the pump, which then in turn sucks water out of the tank and shoots it down the nozzle. For the nozzle, we use 2 servos, one to control x-axis, one to control y-axis. The actual positioning for these servos is determined based on hardware PWM signals that are generated using the Raspberry Pi. These signals are sent through GPIO pins, which then control the position, and the servos themselves are powered using this power supply. Next up, we have our motors down below. The motors are controlled using this board right here. This board's an L298 dual H bridge motor controller board. We control the motors using software PWM signals, which are sent through GPIO pins to this board, which then redirects the PWM signals at the proper voltage to the motors to control speed and direction. We power this board using the 12-volt battery below, and then we use 5 volts from this board to also control the logic on this board as well. Finally, we have the camera. The camera is connected to the Raspberry Pi using a ribbon cable, which sends it in the proper format for the Raspberry Pi to interpret. On the bottom of this power supply, we have an INA 219 circuit, which is able to read the voltage and current coming from this power supply. We are able to then send that to the Raspberry Pi and display that signal on the client. This is another INA 219 board we weren't able to actually fully implement that we wanted to use for the bottom battery. We also have these 5 water level sensors on the back, which we use to determine the actual water level within the tank, and those are just binary signals that we send also to GPIO pins.
I'm going to be talking about the CAD design for our system. Our whole body of the system was made using 3D prints that were designed using the Autodesk Fusion 360 software. This software allowed us to create mini models and iterate them as fast as possible, since we are constantly changing from our design of the robot. A little quick overview. As you can see on this left image, this is most of our 3D components put together into one. And on the right-hand image, this is our robot fully printed out. The only parts that aren't printed on this robot are, of course, the hardware components and the chassis that the robot frame is mounted to on the bottom. But diving into the iterative process of the 3D prints is many of these iterations came through and were done from having to buy new components for the system and having to rearrange them in different orientations. And as we added more components, we started to run into some issues, some of which is like almost they need to be placed in more optimal path for the wires, or such things such as noise started to come into play. And when noise started to come into play, we had to start making more decisions on where to optimally place these hardware components on the 3D prints themselves, and where and how to separate the higher voltage and higher power components from interacting with the signal wires. And from the bottom right hand image, you can see this is our final top board image, but you can see a lot of the components are placed on that backhand side of the board, and that was to make sure that none of the wires were crossed with the voltage components for the signal wires. But diving into further with more of the 3D system designs, we printed the whole water system, and those were some of our most impressive prints because that allowed us to get the whole water system portion running up from scratch. The water tank itself went through a couple iterations. The first iteration used a slant on the inside to feed the water, and this water seeped through this infill, and we decided to go with the flat design with a higher infill percentage to make sure that the water was held tight and there was no water leakage. You can see on this left-hand image, we used two nozzles. One nozzle was a Mr. nozzle, and the other one was just a stream nozzle. And we made sure the concavity at the ends of the nozzle was smaller than the inside diameter of the tube, just so that the stream could sprout at higher pressure. And we also added a spiral on the inside of the nozzle itself to make sure the mister spray out in a fan orientation. The bottom left-hand component is a tube connector that connected the pump to the water tank reservoir itself, and this allowed the water to flow in 290-degree orientations and made it to where the tube didn't have to be bent. We adhered this tube connector to the silicone tubes itself with hot glue, and this made it to where the water pressure from the pump couldn't pull excess water and make it leak through the system. Diving into our water level sensors, we use 5 water level sensors in a vertical orientation to display on our GUI interface increments of 20% of where the water is filled at. This was done using this binary signal system of the GPI through the GPIO pins on the Raspberry Pi, and allows the user to see where the water is at and when they need to refill it. But yeah, this is the CAD design process and all the systems that were set up with it.
The basis of our water system is the water pump. This pump was originally designed to be put in the hull of a small boat and pump residual water out of the boat. We decided to use it since it was the best combination of form factor and power. It runs off of our 12-volt lithium-ion battery and is controlled by a relay on the top level of the robot. We needed a way to focus and aim the pressurized water as it exits the pump. We used pieces of clear, flexible tube and attached that to a hardware store 1/4-inch plastic nozzle. We decided upon a 2-axis servo motor gimbal. One servo controls the left-right motion, the other controls the up-down motion. Our servo motors are controlled by a hardware PWM signal from the Pi, which gets input over the network from the computer controlling the robot wirelessly. Our original servo motors could only move the weight of a couple grams each and were both really twitchy, so we upgraded to much larger servo motors that could handle a couple tens of kilograms. This made it so our nozzle could be moved easily even when it was full of water and being pressurized. We 3D printed a few custom nozzles, one that would spray in a mist configuration, the other in a stream configuration. These nozzles were attached to the servo motors by another custom 3D printed mount. We then needed a place to store all the water so we could have a true mobile robot. The water tank is also custom 3D printed and features a sliding lid so that we could easily refill it with water while also not sloshing water all over the robot while it is in motion. We integrated 5 water level sensors that produce a high or low signal depending on if they are submerged in water or not. These signals are fed directly into the Pi, which sends that data to the remote computer and displays on the user screen how much water is in the tank. We decided to route the water tube around the back perimeter of the robot and hang the water pump slightly off the back of the robot so as to reduce any chance of water accidentally getting on any of the other electronics.